Good afternoon and welcome and thank you for joining us today for the Bicentennial Alliance Lecture Series. My name is Melanie Keeney and I am the Director of Engagement and Outreach here at Missouri S&T. Today I will serve as your host and moderator. Missouri S&T is currently celebrating its 150th anniversary, coinciding with the Missouri Bicentennial celebration. As a way to honor Missouri's bicentennial, S&T is hosting a lecture series titled Honoring Our Past, Envisioning the Future, Missouri S&T's lecture series for the bicentennial. This series celebrates the rich cultural history of our region and explores social and economic growth topics relative to Missourians. Today, we present the first of this series titled Mining from Missouri to the Moon. Before we get started, I'd like to go over a couple items with you. Today's speakers welcome your questions. If you have a question that you would like to ask, please type it into the Q&A box. Questions will be asked in the order in which they are received. Please note that the chat function will be disabled during this presentation. As a thank you for your participation today, we will be randomly selecting a viewer to receive a gift bag. This gift bag will include promotional items from the Missouri Bicentennial, as well as from the Missouri 150th, and this beautiful book by our own Dr. Larry Gragg, Forged in Gold. And with that, I would like to welcome our three speakers today. Dr. Larry Gragg, Curators, Distinguished Teaching Professor Emeritus here at Missouri of History and Political Science here at Missouri S&T. Dr. Alana Krolikowski, Assistant Professor of History and Political Science at Missouri S&T, and Dr. Leslie Gertsch, Associate Professor of Geological Engineering here at S&T. And with that, Dr. Gragg, I'd like to turn it over to you.
Thank you, Melanie. This is a treat to be on this panel. I'm really looking forward to what my colleagues are going to talk about here in just a little bit, because they're going to be talking about the future. My task is to talk about the past, specifically the past involving the Missouri School of Mines and Metallurgy, University of Missouri-Rolla, and Missouri S&T, and how it became one of the premier undergraduate mining engineering schools in the country. A second reason why I'm excited to be part of this panel is I've been so involved in researching and writing the history of our campus for our 150th celebration, and if you can't tell, I'm really attired in everything that's 150th for Missouri S&T. So what specifically am I going to talk about in my 15 or so minutes? I want to tell you why there was a School of Mines and Metallurgy for the state of Missouri and why located in Rolla, Missouri, when it could have been located in many other areas of the state. I will discuss some of the really challenging days for this campus in its first 25 years, and then look at three directors of the campus who between 1897 and 1920 literally turned around the fortunes of the campus. And by that last date, 1920, the Missouri School of Mines and Metallurgy was the premier undergraduate mining school in the country. And then a few remarks about the lasting reputation of MSM, UMR, and S&T. So first, why in the world would there be a School of Mines in the state of Missouri? And it has to do with a piece of legislation that was signed in 1862 by President Lincoln, and the bill was called the Morrill Act. And the idea behind it was, how do you provide access to higher education in the United States to people who otherwise would not be able to go to college? And in particular, the legislation referred to how do you give access to the working classes of the United States? And they believe the solution was to create two kinds of colleges. One, a college of agriculture, and the other was to create colleges that we would call schools of mines and metallurgy. Now, Missouri was willing to participate in this, and for participating, each state would get land grants to help fund these institutions. Now, in the state of Missouri, legislators debated for about 8 years, trying to figure out where are we going to place the College of Agriculture, where are we going to place the School of Mines and Metallurgy. And after this 8 years of debate, they decided the College of Agriculture would be placed in Columbia, Missouri, where there was an existing university that had been there for just over 3 decades. But as far as where to put the School of Mines and Metallurgy, they decided to open it up to every county in South Central Missouri and Southeast Missouri for a bid. Whichever county came up with the highest bid in land and cash and bonds would get the institution. And Phelps County just barely nosed out Iron County and won the right to locate the School of Mines and Metallurgy in Rolla. And the campus begins offering classes in November of 1871. And we're really looking forward on this campus to commemorating that this fall. One building, we leased a building that was constructed by the Rolla School District, and we would have only one building for about 15 years on this campus. The challenge in those first 25 years is how do you recruit students who are adequately prepared to do collegiate level work, because there were almost no high schools in Missouri outside Kansas City and St. Louis. In fact, we had very few students who could do the science and the math, let alone the engineering courses in the first 25 years. So you could enroll either as a regular student, that is, you met the requirements for admission and you took the whole curriculum, or you could enroll as a preparatory student, which was in essence being like a junior and senior in high school, and you focused on arithmetic and beginning algebra, so you'd be ready for college algebra. Or you could enroll as a special student. You could take any array of courses you wanted, hoping to get a certificate of proficiency. Most of the students in the first 25 years were preparatory and special students. So this campus, through 1892, when there was a study published of all the degrees granted in mining and engineering across the country, there were 16 colleges granting degrees, and altogether they had granted 871 degrees in mining and engineering, and the Missouri School of Mines was eighth. It had only granted 26 degrees in the first 21 years of its existence in mining and engineering. Its impact was minimal. There was some discussion that perhaps it might be time to close down the Missouri School of Mines. But just at that moment, the campus has the great good fortune of having three directors, George Ladd, Lewis Young, and Austin McCrae, who literally turned around the fortunes of the campus. They did several things that made this a premier institution. One, they got enough appropriations to begin hiring more faculty, and faculty who increasingly had the PhD, which was uncommon. They gained funding to build several new buildings, two of which we still use, Parker Hall, which is our administration building, and Norwood Hall. They raised the admission standards, but still increased the enrollment of the campus. And they brought to the campus the Missouri Geological Survey. They started an experimental mine station in 1909 and established a journal so the professors doing research there could publish the results of their research. The establishment of an experimental mine so students could more readily understand the mining profession. And the big one, 1920, negotiating with the new Federal Bureau of Mines to have one of their experiment stations located in Rolla on campus. And because of that successful negotiation, the campus was able to lobby the state legislature to build yet another building, which we still use. It's called Fulton Hall. That's where the Missouri Bureau of the Bureau of Mines was located for about a quarter of a century until we built a new structure just off the campus. Well, what happened as a result of this? The reputation of the campus went up dramatically. In 1896, the president of the Michigan School of Mines had concluded that the Missouri School of Mines was little better than, as he put it, a country academy. It wasn't really a true mining school. But just 11 years later, after George Ladd and Lewis Young are putting in all these remarkable reforms, the president of the Colorado School of Mines printed a study of the pedagogy and mining engineering across the country and concluded the following. He said, the great private institutions, Columbia University, Harvard University, and MIT are doing excellent, excellent work. But so are 5 of the state schools, notably in California, in Colorado, in Michigan, in Minnesota, and in Missouri. So the reputation of the campus has dramatically improved. And what it leads to is a rapid increase in enrollment. in looking at the statistics from the second decade of the 20th century, what you see in the academic year 1911, among its competitors, the Missouri School of Mines is third among South Dakota School of Mines, Colorado School of Mines, and the Michigan School of Mines. But just 4 years later, far and away, the Missouri School of Mines is ahead in total enrollment. And by 1920, the campus has more mining and metallurgy majors than any campus in the United States. It has become the leading institution in producing students who get degrees in mining engineering, and that will continue well into the rest of the century. In fact, at mid-century, the academic year 1949 and 1950, the Missouri School of Mines was far and away the leader. West Virginia was a distant second, and the Colorado School of Mines was a distant third. Now that has continued well into the 21st century. I was looking at the statistics for the year 2020, and only Virginia Tech and the Colorado School of Mines awarded more degrees in mining engineering than did Missouri S&T. So what's the impact of all this, having all these students? Well, minor alumni spread out across the country. As early as the first publication of a listing of alumni who had degrees in mining engineering, which was in 1906, they are located in 16 states across the country. They're in 2 territories. They're located in several foreign nations, including several in Mexico. And that just continues to broaden with each passing decade. And the graduates of the institution are in such great demand that every year when the campus registrar reports how the graduating senior class is doing, they wrote with great accolades how easy it was for the seniors to get jobs. I'll give you one example. In 1928, which was a very good year for graduates, the assistant registrar reported that every single graduating senior in mining engineering had a job secured on the day of graduation, with 2 exceptions. And those 2 students had opted to continue their studies, so they were not in the job market. And he further reported that based on phone calls and letters from companies in Missouri and in Texas and in Nevada and from Mexico, he could have placed at least 50% more of these students because the demand was so high for the graduates of the Missouri School of Mines and Metallurgy. And if I had unlimited time, I could tell you about many of these alumni, but I'm going to focus upon just one of them, who technically was not a mining engineer from this campus. He was a metallurgical engineer, but his career was in mining. And his name was Daniel C. Jackling. Jackling was from a very poor background, grew up near Appleton City, Missouri, but went to high school in Sedalia, Missouri, spent 1 year at the State Teachers College in Warrensburg, what is now the University of Central Missouri, transferred to the Missouri School of Mines as a preparatory student. He didn't have the requisite math and science courses, but quickly caught up, and he graduated in 1892, and he went west. And he was involved in mining of all kinds of ores, notably gold mining. But then he got an idea that there ought to be a way that you can more efficiently process low-grade copper ore. And he had observed how there had been so much success in the mining of iron ore in Minnesota, he was able to transplant those processes to what becomes the Bingham Canyon open pit copper mine in Utah. It is a massive open pit mine. And it's so important to the state of Utah. If you walked into the state capitol building now in Utah, you would see this magnificent statue of Daniel C. Jackling. And he was a great philanthropist for this campus, known widely as one of the richest men in the country in the 1920s and 30s. He gave money for athletic facilities at the Missouri School of Mines, and he started a really important student loan fund. And he gave great visibility to the campus for how he spent his great riches. He had, according to the contemporary records, a yacht that was just short of 260 feet long. And when he was traveling cross country by train, he had his own private railroad car. And he and his wife, before they built a mansion just outside San Francisco, California, they leased the top floor of a hotel in downtown San Francisco. Not that it's important that he was that rich, but every time there was a story about Daniel C. Jackling, his name was linked to the Missouri School of Mines and Metallurgy, and it helped elevate the visibility of the campus. So what happens here, particularly in the last 120 years, if we discount those early years of struggle, what happened in Rolla, Missouri was the establishment of the Missouri School of Mines and Metallurgy, which becomes the University of Missouri-Rolla in 1964. And then in the 21st century, Missouri University of Science and Technology. What happens is the emergence of one of the nation's leading undergraduate institutions in mining engineering. And why that's important for today's panel is that many of the students who have gone here or who are currently here are going to likely be those who participate in what my two colleagues are going to talk about next. That is mining beyond planet Earth, mining on the moon. So with that, I'd like to hand off the panel session to my colleague, Leslie.
Thank you, Larry. It's good to hear a review of what we've accomplished here at what's now Missouri S&T. And I'd like to change the focus a little bit towards what we can do in the future, because mining is not just a thing of the past. Responsible use of resources is not just a thing of the past. It's what we are doing going forward and what we think that our students and our graduates and our alums will be doing in the future. We've got, let me grab my notes here. You probably have seen the news where the Perseverance rover actually landed on Mars just last Thursday, joining a number of rovers, only one of which is active, Curiosity, Opportunity, Spirit, and even Pathfinder, the little tiny one. And they're getting ready for humans to go back to Mars in the 2030s, which is not that long ago. In fact, there are plans for people to go back to the moon in the 2020s, and here we are in 2021. So there's a lot of need for sustainable exploration and use of the natural resources of space, doing the science investigation of space. But to be sustainable, to actually be there for any period of time, you've got to be able to live off the land. And that's what agriculture and mining is all about. There are different technologies, different methods and approaches that we can adapt from here on Earth. Oh, and I also forgot to mention there's a bunch of asteroids that are actually easier to get to than the moon from an energy point of view, which is what counts in space more than actual distance. Let's see, is permanent human presence, whether it's for exploration or making money or doing science, and those things are not independent of each other. They're going to need people who are trained in mining and aerospace, and we're one of the few mining schools that actually has aerospace in our curriculum. And it's time we can actually, and we're starting to develop a hybrid discipline. I'm calling it space resources, but who knows what it'll end up being called, that includes mining engineering, materials science and engineering, chemical engineering, geology and geophysics, all sorts of sciences. And especially there are the regulatory and legislative aspects. The mining law of 1872, how will that be different? How can we apply that in space? Anytime humans move into new territories, new in some sense, then we look to find ways to support ourselves, especially in space, because we're limited in mass that we can launch. We're limited with the energy that's available, but with the technologies that we can develop here at Missouri S&T and other schools across the world, we should be able to have a lighter footprint on the earth, partly by being away from it and partly by developing new technologies. And I see this as something that Missouri S&T is uniquely situated for. People who are practical like Missourians are, the show me state. We have a team of Missouri S&T students that right now are working on the NASA's Break the Ice Challenge. Our team name is Show Me Ice. And we've got people who are interested in applying mining and processing technologies, not just the way they've always been done, because they weren't always that way. We've developed these mining methods over several thousands of years. There's some evidence of mining even 300,000 years ago. And we've looked at it and developed different techniques, and many, in fact, you could even say most of the advances that have been made in mining are people working at the mines, figuring things out. And that's why the United States made the effort to fund schools like this, as Dr. Gragg was just mentioning. And we will continue to need this into the future. There are major differences that we have to consider when we look at translating current practice here on mineral production here on the earth to spaces off the earth. And I'm sure you know many of those. The gravity is different. On the moon, it's 1/6 of what it is here on Earth. On Mars, it's about 3/8. Asteroids are in what we call generally microgravity environment, where it's essentially zero and you don't really orbit anything. You just sort of keep yourself in the vicinity thereof. And you don't land on little tiny bodies like that, but you do land on places like the moon and Mars. And that's how we get there is going to change the mining methods that we're going to have to develop. But of course, we need to start with what we know. There will be different atmospheres. And that's not just vacuum like on the moon, but thin atmospheres like on Mars, atmospheres that have different gases than we're used to and different pressures. Things like carbon dioxide on Mars and on Venus. But on Venus, the atmospheric pressure is just crushing. It's terribly hard to do anything on Venus because it's hot and it's very high pressure. How's that going to affect things? What can we do there that we can't do here, and vice versa? We've got liquid water here on this planet, and we take it for granted because it's everywhere. Of course, actually, we live pretty much at the triple point. We can have ice like we did last week. We can have liquid water like we're having now, and we can have humidity in the atmosphere. But the biggest change is really going to be the fact that we have an atmosphere. And the thermal effects of having this blanket of air that convects, that moves with differences in temperature, is something that we definitely take for granted. We don't think much about it, but when we go to do mining and processing on the moon, on Mars, and on asteroids, we're going to be missing that, or at least it's going to be very different. How are we going to deal with that? On the other side of that is, how are we going to actually obtain the material that we're looking for? Are we looking for water ice? Right now, that is the big target material, because that can be turned into spacecraft fuels and propellants, as well as, of course, life support gases, oxygen, hydrogen, which is used for manufacturing, and water, of course. Water is also a very good radiation protection medium and mechanism. So all of those, they don't sound as fancy as gold or diamonds or rare earth elements. And although those will someday be of very economic importance, right now, finding water, whether it's in the form of ice, which has been detected on the moon and of course on Mars, and Mercury too, believe it or not, but also hydrogen and oxygen that are part of mineral structures. And with various different means of processing, they can be extracted from those minerals and used for those same desires and needs that we need to be there in space sustainably. For right now, we're just starting. We have a space resources graduate certificate, but we're hoping that that will grow into degree programs, both undergraduate and graduate, within the next few years. I believe that Missouri S&T is going to be at the forefront again of a whole new approach to obtaining the materials that we need for civilized life, so for human civilization, while at the same time taking better care of the environment in which we live here on Earth. So, of course, as I've mentioned, there are regulatory and legislative and policy implications for all of this, of how these are set up. And for that, I'd like to pass off to my colleague, Alana Krolikowski.
Hi, hello everyone. Thank you very much for having me. Thank you, Leslie. I'm gonna go ahead and share my screen here with some slides. So I'll ask our organizers to let me know if that my images don't come through. So thank you so much for this opportunity to address you today. I'm going to pick up where where Dr. Gertsch left off, and just give you one illustration or one example of the kind of interdisciplinary research into the future of mining and mining on celestial bodies that she talked about. The research or my remarks today are going to draw on a research collaboration that has now been ongoing for several years with an astrophysicist, Dr. Martin Elvis at the Harvard-Smithsonian Center for Astrophysics, and an ethicist, Dr. Tony Milligan at King's College London. So in so doing, I hope I'll kind of broaden the aperture on the type of research that finds a home here at Missouri S&T and speaks to the future of mining. And I'll also kind of give you a sense of the kind of interdisciplinary work that can take place in this area and that has a role in informing how mining evolves in the future. So let me start off by saying that I'll confine my remarks to the moon today, but most of what I'm discussing can be extrapolated in some way or another to other resources. I'll tell you a little bit about our research on lunar resources, some of the implications of our findings, and the kind of policy and governance considerations that those findings raise. And I'll kind of give you a sense of what a discipline like political science or with an ethical perspective can contribute to discussions about the future of mining in space at the final frontier. So we know today that the moon has resources that might someday be attractive for us to mine. And furthermore, as our understanding of the lunar surface and the lunar subsurface has improved with successive missions to the moon, we've learned that those lunar resources are certainly not evenly distributed throughout the moon. They're actually concentrated in a few tiny little patches of the moon. So I'll talk to you in a few minutes about how exactly those resource concentrations look and why they're important. But I'll foreshadow you now for you right now that what's important about the concentrated character of lunar resources is that we might be on the cusp today of a lunar renaissance. We expect to see in the next decade or so a flurry of missions to different destinations on the lunar surface. Maybe as many as 8 to 12 within the next 5 years, and more numerous missions expected after that. So we're really on the cusp of a period of intense lunar activity and many upcoming lunar missions that will converge on these concentrations of resources or other sites of interest on the moon. Those will be international missions. They'll be sent from places like the United States, Russia, Japan, India, China, maybe Europe. They will be public, oftentimes launched by agencies like NASA, and maybe for the purposes of scientific discovery or in order to establish a human presence on the lunar surface, for example. But they'll also be joined by missions sent to the moon by private companies like iSpace in Japan, for example, that have all kinds of designs on the lunar surface, which might eventually include, or we expect to include, lunar mining. So let me give you a sense of the destinations at which these future missions are expected to converge, probably within our lifetime. This here is a map of helium-3 deposits on the Moon from the Indian mission Chandrayaan. What's remarkable about this map is that you see here that helium-3, which would be the kind of material that we might want to mine on the moon because it would have applications in energy production. Helium-3 is concentrated in a few tiny little spots on the lunar surface. They're little red spots. Those areas are tiny as a proportion of the lunar surface. They're about 5 to 50 kilometers across. And crucially, they happen to be co-located. They happen to be close to ideal sites for locating telescopes that could do radio astronomy, especially from the far side of the moon. But those areas are uniquely valuable pieces of real estate on the lunar surface, not only for mining, but also exactly for these other kinds of scientific purposes. And yet those purposes cannot be simultaneously pursued. We couldn't both place an operational radio telescope near these helium-3 deposits and actually mine them. We couldn't operate a telescope if we were mining nearby. So these little deposits of helium-3 illustrate the concentration of lunar resources, but also the fact that these patches of resource-intense lunar areas are co-located with interesting lunar features or other kind of topographical features that present special utility for other types of missions. So there's a few truly high value patches of lunar real estate that are uniquely attractive for both eventual mining missions and other kinds of missions, including scientific ones. This is an illustration of the deposit or the distribution of helium-3, but you can imagine an analogous situation arising for other materials that we might eventually mine on the moon, like uranium or thorium, or even water ice. They will be clustered at tiny, tiny areas. This here is another example of a lunar site of interest that is likely to attract numerous missions to it in the coming decade or so. The rim of Shackleton Crater here at the lunar South Pole is an example of a peak of eternal light. It's an elevation on the lunar surface that is almost permanently illuminated by the sun. And that makes it an area of unique and strategic importance on the moon, because emplacing solar panels there would give an actor an almost unlimited or virtually unlimited stable supply of energy, which in turn would be enormously valuable for any other type of activity, whether it be mining or building a human settlement or maybe undertaking some kind of, installing some kind of scientific instrument. Right by the peaks of lunar light are cold traps. The coldest of the cold traps are very, very few in number. They're also clustered in a few small places, and they're possibly of incalculable scientific value. These are depressions in the lunar surface that are not illuminated by the sun, so they get very, very cold. The very coldest of them could contain materials that are volatiles normally on Earth, but that are in liquid or solid form there at those extreme cold temperatures. And there are also areas that could yield really invaluable insights into the formation of the moon and therefore the formation of our solar system. So these are other pieces or areas of high value real estate on the moon that are likely to attract forthcoming missions. Finally, another kind of lunar site of interest or another kind of lunar feature that we can expect to attract missions in the future consists of the lunar pit. Lunar pits are found in different areas. They are depressions again in the lunar surface, but they present unique features that make them especially valuable for certain types of missions. We know of at least 221 documented pits that are especially interesting, but the ones that are really the most valuable for future lunar missions present this combination of distinct features. They're easy to access. They feature these large overhangs, which mean that large parts of the interior of those pits is sheltered from radiation and light. And they're also near resources. The kinds of lunar pits or the pits that satisfy those three criteria are actually very rare, and they probably number well under 10. So those pits are, again, uniquely important lunar features that are likely to attract several missions in the coming, let's say, decade or two. So the picture that emerges from kind of what I've described to you here, these concentrations of resources that are co-located with interesting topographical features on the moon, what that really portends in combination with this flurry of upcoming missions is the likelihood of crowding and interference at some of these high value sites. So we can already tell that that's the case because the lunar sites of interest are very few and they're very small. On the other hand, the missions that are targeting, that they're expected to target these sites are many and their mission footprints are expected to be very, very large. So we can already tell at this point that there'll be a challenge, or there's a likely challenge on the horizon of coordinating and managing activities at these different sites so that different users don't act at cross purposes, so that they don't inflict interference on each other unnecessarily, and most importantly, so that on the whole, we minimize the collective loss of opportunity, scientific and otherwise, that would result from an uncoordinated rush of missions to this handful of very interesting sites. So that's kind of where our research comes in. And maybe I'll just characterize for you the kind of interference problem that we can imagine arising. Dr. Gertsch is ideally positioned to tell you about this, but one form of interference has to do with dust. When spacecraft land and take off from the lunar surface, they create enormous disruptions in the dust, and they kick up a lot of dust that then proves to be a terminal enemy of a lot of equipment and is likely to obscure solar panels and inflict other damaging consequences on nearby instruments and installations. So just dust interference alone is a really, really significant form of or collective action problem to address. But there are other types, radio interference, for example, as we discussed, and also just the destruction of scientifically valuable features. So that's where our research comes in. We've kind of looked at this problem and tried to characterize the likelihood of crowding by examining the concentration of the resources and the kinds of activities that those sites might attract, and anticipating the problem of crowding and interference. We've looked to terrestrial environments for lessons in how we could mitigate or manage those crowding and interference challenges. So we've examined what we call common pool resources, or commons on Earth, areas where multiple actors have access, but no single actor has exclusive control or ownership of the resources. You can think of, for example, Antarctica as that kind of commons, or you can think of a fishing stock in a pond that's jointly used by several villages or villagers as another example of a commons on Earth. So we've looked at different environments like this at different scales. We've looked at international regimes all the way down to very small local institutions and management practices to see how people have, across time and space, overcome the challenges of crowding and interference at sites of concentrated resources that are held in common. And so we've tried to distill the insights that we can draw from this terrestrial experience for the moon, and for what it could mean for how to responsibly manage these challenges on the moon. And what we've learned is that there are already successful models for managing commons to some degree on Earth, and there are ways to design platforms that aid in that management that are likely to evolve with new technologies that are able to accommodate new and diversifying users. And we do well to emulate some of the, or at least try to develop similar platforms to address crowding at the moon. We know that actors on Earth tend to perform better at joint management of resources or cooperation, other cooperative projects, when they hold firmly in view the kind of worst case outcome that they all share an interest in avoiding. So one of the things we're focused on is how to characterize those kinds of worst case outcomes and build consensus on avoiding them among prospective lunar actors. We know that actors tend to cooperate more effectively when the future casts a long shadow. So in particular, when actors expect to interact with each other repeatedly, and when they expect their behavior to have long-lasting consequences. So we've explored how to design institutions for lunar governance that would achieve some of those effects. We also know that on Earth, early practices end up being highly consequential precedents that greatly increase or have a long run impact on later outcomes. So we know that early instances of cooperation greatly increase the likelihood of later forms of cooperation among actors in different kinds of terrestrial systems. So we want to emphasize to any lunar users that the very first missions will set expectations for conduct and practices that are likely to greatly outlive or outlive those early missions by many decades, and really set the stage for long-lasting patterns of interaction. And we're also exploring how to change incentives so that actors on the moon are most likely to abide by any kind of cooperative or governance arrangements for how to jointly utilize some of these sites. So we've thought about how we can extrapolate some of these lessons from Earth and incentives for cooperation used on Earth to a lunar setting. One of the ideas, for example, that's developed from that is the idea of building lunar landing pads that would mitigate dust disruption, mitigate the kicking up of dust, and to make that kind of common lunar infrastructure essentially an incentive for collaboration by making access to that shared lunar infrastructure conditional upon compliance with and respect for norms of conduct or other rules about how to behave at these different lunar sites. So I will essentially wrap it up there, but I'm happy to pick up on any one of these threads in Q&A, and also to kind of invite any contributions from my co-panelists to this set of ideas. So thank you very much.
Great. Thank you so much, everyone, for your wonderful presentations. Let me start my video. Sorry about that. And now what I would like to do is open it up to our participants to ask questions. If you have a question that you would like to ask based on what you have heard today, go ahead and drop that question into the Q&A, and I can report that out to our speakers. Kind of give you guys a couple minutes to do that, to input your questions.
Well, while people are thinking of questions, I have one for Alana. How do you see the shared policies being developed for use of on the moon or the resources of the moon, given the various different types of outcomes that we've seen in past history in different mining regions and so forth? How do you see it actually going forward from here?
Yeah, that's a great question. And I think when we talk about the future of lunar governance, let's say, or a really big topic like that, which includes, of course, what I've just talked about and the kinds of topics that you're focused on, we usually imagine several parallel processes. On the one hand, we already have the basics of a global governance structure for human activity off Earth. We have an outer space treaty, and we have international bodies that convene experts and participants, representatives from different national space agencies. And we have other bodies that kind of set rules and expectations for what responsible conduct in outer space looks like. Those processes are indispensable and necessary, but they also advance on multi-decadal timeframe. Right, much like global climate negotiations, these are very slow-moving, deliberative bodies that typically try to create binding new international treaties. And when they try to do that, they necessarily undertake a very, very long consensus-building process. So we're sure that that work should and will continue in parallel. The kinds of concerns that we're interested in are short and medium term problems that we can all expect to read about in the news headlines within our lifetimes, within a decade, within 2 decades. So we believe that there'll be a need for much smaller scale, more agile, and more nimble processes to address the kinds of specific crowding and interference problems that we see at these very particular sites that I've just described. So we anticipate maybe the creation of kind of user bodies or other fora or platforms that would convene specific users of local sites on the moon to try and manage those problems. And then we imagine that it would be helpful to have those different local processes be guided by a common set of principles and kind of procedural norms so that there's some measure of consistency across these different structures. and that we kind of balance tailoring solutions to specific local sites with their own unique demands, but also ensuring some level of, let's say, lunar level kind of consistency in procedure and principle. So I think for us, that's probably one plausible pathway forward, but it's certainly not the sum total of what will happen. And there are many different efforts to characterize what should happen and even just conceptually how to think about these problems.
Thank you.
Great, thank you for that. We have had several questions come in. So I'm going to start with the first one here. How soon do we imagine being able to mine materials from the moon? And which country do you think would be the first?
Ooh. Well, actually, technologically, we could actually mine materials from the moon right now once we get back there, but it would be highly inefficient. Which country would be the first? You know, China's giving us a pretty good run for our money. So I think it's a toss up right now between the United States and China. Korea's got designs on the moon. Europe certainly does. Japan, and of course, Russia. So it's hard to say.
Thank you. All right, our next question. The history of science fiction is full of mining the cosmos with various outlooks and perspectives. Can you discuss the ethics of a human workforce in such dangerous environments and with the outlook on and cooperation with automated drone developments?
Well, I can take a first very general stab at that and then hand things over to Dr. Gertsch. I think there's a growing consensus that we cannot reproduce the errors of the past in the future. And that the way we talk about mining today, whether it's mining on Earth or mining on celestial bodies, and the way we talk about the environment today and impacts on peoples and nature today cannot sound like the way we talked about it 200 years ago. So I think the space community right now is in the process of kind of evolving and growing more sophisticated about how to conceive of human settlement in space, how to maybe distance itself from these familiar tropes of colonization and exploitation, and how to think about a different model of extending human presence and a different kind of human environmental relationship. So I think that I think is, we're at the early stages. And if you're a student at S&T, you will be part of the generation that really defines that conversation. You'll be the one that fleshes out how we do it better going forward and beyond Earth.
And Larry, could you describe for us some of the differences maybe between how we're trying to become more responsible, some differences between that and the very profit focused perspectives that have been in the past when the school was much younger than it is now?
Yeah, that's a terribly important question. The idea of environmental costs really did not cross the minds of most of these early generations of minor alumni. It didn't occur really to the gentleman I mentioned, Daniel C. Jackling, and the companies that followed Jackling in controlling the Bingham Canyon mine discovered enormous environmental damage to the entire region around that mine. So it's something that really develops it in the 1960s, a more environmentally conscious generation, and it really has multiplied with subsequent generations. The way that mining engineering is taught in 2021 is dramatically different than 1921. So I agree with Professor Krolikowski that there's been a lot learned in the past 200 years, and there's a very different mindset that's looking at how do you do this properly, whether it's on Earth or on the moon.
Mm-hmm.
Great, thank you. Next question. As mining becomes more prevalent on the moon, what considerations would need to be made with regard to changing the moon's mass and the effects which can occur within its delicate gravitational balance with Earth?
That's a very responsible perspective. The moon is certainly smaller than the Earth. The diameter of the moon is only about a quarter that of the Earth, but that still means it's the size of Australia, and Australia is a really big place. So here's a model of the moon, and it would be, goodness, I don't know how many millennia it would be before the changes in mass, and of course most of the mass would stay right here on the moon, but even assuming we took all of the water away, just away from the moon, it would be thousands and thousands of years before there'd be even the most tiny measurable change. So it's not, I think there are probably other aspects of sustainability and responsibility for environmental aspects that would probably become important before that would happen. Of course, that being said, it's not something we should forget and ignore.
Alana, this question is specifically directed towards you. What are societal gaps to realize moon colonization?
Yeah, I think that's a fascinating question that intrigues all of us. I think the first one should be why, to what end, with what, guided by what values, and in view of what consequences. I think we're still not there. If you look at debates within the professional space community, since the Apollo program, really, I think we've witnessed a lot of deliberation and many, many different ideas of what human settlement of new destinations in space should accomplish. Is it scientific? Is it to lift the human spirit? Is it because humanity yearns to discover? What is ultimately the goal? I think we're still having a nationwide and a global conversation about what exactly is the higher purpose served by human settlement, because extending presence for that sake alone is probably not sufficient enough anymore for at least some key stakeholders. And it doesn't probably rise to the level of responsible conduct in the way at least most people increasingly think of it now. So I think that's probably the first gap, is a kind of consensus on purpose and a really mission in a big metaphorical sense, not just the actual program management of a mission. I think that's a big problem. And then once that purpose is clarified, I think we'll have a sense of what defensible resource allocations to that end look like. Why do we do it will help us understand to what extent we support it, at the expense of what other public interests do we fund those activities. So I would say that's a starting point, but of course that's really just the beginning of a very, very big, and I think ongoing conversation. You could ask a lot of space people whether going to the moon is the right idea, and they tell you, we've done the moon, and actually we should really be aiming further. We should be focusing our energy on Mars, for example. So again, I think that field is unwritten. And I do think, yes, the obstacles that are social, political, and kind of cultural are just as significant as the technological ones.
Larry, this question is for you. In the old days of schools of mines, was there a competition to claim the name miners?
No, not really. There was this community of mining schools. It was small and it remained small. The idea that you have a school of mines on a campus that has also a wide array of engineering disciplines is something that was relatively unheard of until the 1920s. On this campus, we offered essentially 3 degrees until 1915. In the first 44 years of the institution's development, we only offered degrees in mining engineering, metallurgical engineering, civil engineering, and then just a general science degree. But then the realization struck, and this is true of mining schools across the country, that if you remain just a mining school, you'll never grow very large. That you have essentially a few hundred students at most. So this campus got a piece of legislation passed in 1915 that permitted the Missouri School of Mines to also offer mechanical engineering, chemical engineering and electrical engineering. And then in the mid-1920s, there was great demand for the offering of ceramic engineering because it was such a large industry in the state of Missouri. So the campus becomes decreasingly a school of mining and metallurgy. In fact, by the early 1930s, the number of students majoring in mining engineering and metallurgical engineering is easily eclipsed by those in civil, mechanical, chemical, and electrical. So the long answer to the question is mining schools tend to disappear within the wider array of degrees being offered on campuses.
Thank you. How is Missouri S&T, or how Missouri S&T is preparing for mining on the moon? And is there any tentative timeline for any specific projects?
Well, NASA is working on what they call the Artemis program, which is first going to construct a sort of a space station in the vicinity of the moon, not necessarily orbiting it, but nearby. And from that would spring, they have plans that I haven't seen, but necessarily, but they do plan to do surface operations on the moon, and also communication and transfer operations for elsewhere, like asteroids and Mars and such like that. It's a timeline that supposedly is, well, it's already underway. Ideally, the next launch to the moon would be around the end of this year. A rover mission, I think it's the rover mission that's going to land and do some prospecting, some geotechnical measurements, because you can't mine something if your equipment gets stuck. So you have to figure out what the land is like for traveling over. And following that and a few more missions, then humans would return. So that's a sort of sequence we're looking at. I don't know what the plans that China has are. I don't know what Russia's plans are. I'm not even certain about Japanese plans, and also Australia is getting into the game. So it's going to be an interesting time for developing the fundamentals, the foundations for policies that are going to have, as Alana said, quite significant implications in future developments.
How far away are we from economically viable space mining? Will it develop with space-heavy manufacturing?
Very likely, maybe not even heavy, but mostly there are potential markets in what they call on-orbit servicing of satellites. And of course, satellites are an increasingly major part of world economic considerations. And if they can send up satellites that don't have to be deorbited, that is crashed, whenever they run out of fuel, then there would make much more efficient this industry and would increase it even more. So there's the opportunity for manufacturing in space using materials from space. And that's going to be a very big one. There's also the defense implications. The new Space Force, for example, is looking at the militarization of space. And so here we've got some definite long-term, very important policy decisions that are going to have to be made, not just on our part, but all over the globe. So it's the heavy industry is going to be part of it, but there's also going to be specialty materials. So you can do sorts of manufacturing and material fabrication in space that are difficult or expensive or even impossible on Earth. So there's going to be multiple aspects of that.
I would just quickly piggyback on Dr. Gertsch's remarks to say that the way this will unfold is in a phased manner, right? So what we see now is actually a small flurry of startup activity around developing multi-purpose rovers, for example. So we'll see the development of technologies that have multiple applications, maybe from multiple different sources, over the next kind of waves of missions. And eventually those technologies could be adapted toward mining purposes, right? So I think we're gonna see this kind of gradually ramp up, and the next milestone on the horizon is not like immediately kind of large scale commercially viable mining, right? But yeah, and I think it'll actually be crucial probably from a lot of those for a lot of those companies to not just maybe target their products at an eventual mining industry, but actually try to capture different market segments and deliver different kinds of services or products beyond mining.
Excellent, thank you for that. Okay, our next question is, won't the cost of getting materials back to Earth in useful amounts be prohibitive? The fact we're talking about this implies the answer is no, but the planning for returning exploratory Perseverance samples from Mars is still vague and hypothetical. What am I missing?
Well, the first markets for materials from space are in space. In fact, you sound like my dad. He's always asking me, when are we going to get the first shipment of ore from the moon? Well, that's far in the future. Basically, living off the land is what you do before you ship products to somewhere else. So that we need to get a foothold, get our sea legs before we actually can think a great deal about exporting space resources somewhere, except for niche things like moon jewelry. I can see that coming right away.
I would add that just another example of an in-space, maybe one of the most promising in-space markets for space-derived resources was for water from asteroids. Insofar as we had a credible attempt at commercial asteroid mining in planetary resources and deep space industries, two companies that are now no longer pursuing that in any strong sense. Insofar as we had any movement, significant movement, it was first and foremost to try and extract water and then use it to produce propellant in space. So mainly to avoid the enormous cost of escaping Earth's gravity well with lots of heavy water to bring it to a vehicle in space.
And that's not so different from the way Missouri developed its mining industry. There are things that we used to mine in Missouri that now really aren't, like barite, for example. And Larry mentioned clay for our ceramics industry. We still mine that. We don't mine very much coal anymore. So things develop, and people 100 years ago would not have foreseen some of the things we mine now and some of the problems that are associated with those. So you can't really look ahead and see everything clearly. As Alana says, it's a phased development.
All right, we've got two last questions. The first one is, there are multiple celestial bodies available for mining and science, such as asteroids or Mars. Why is the main focus on the moon?
So I've written about asteroid mining in the past. I think some of the questions are common actually across celestial bodies, and some issues really are specific to the moon. I think for us, the moon is especially interesting right now because I think we may in fact be on the cusp of a lunar renaissance. We may be seeing a flurry of missions to the moon within the next decade, which means that these resource questions take on new significance and new urgency right now. But I think long term, that a lot of the issues extend to asteroids, and some of the earliest enthusiasm we've had for serious space resource mining has really focused on asteroids initially. Part of that, I think, reflects the fact that NASA's programs really set the tone for the commercial space industry and for a lot of commercial energy still, even though we think of commercial space as so very, very dynamic. But when NASA really turned its attention back to a large scale, reinvigorated lunar program, you saw a lot of commercial business piggyback and kind of reorient some of its pursuits toward the moon, as opposed to asteroids, which had been given more attention and more resources by the previous administration.
And if you go back in history, there have been several pushes for the moon, obviously the one at Apollo days, but also in, oh, let's see, 2004, there was a big push towards the moon, and then push towards Mars, and then back to the moon with a little bit of asteroids in between. There's a lot of politics involved. It's not just the technical part. It's more the economic and other human civilization aspects that drive that. It's not just technology.
Has there been any international discussion regarding the establishment management of mining claims on the moon?
Yes, there have been proposals for, well, I don't know if mining, there have been proposals for things like lunar registries and other mechanisms by which actors with designs on specific locations of the moon would register their interests, share their plans, and stake a claim to access. So there's a kind of, I mean, this is a time really when people are coming up with ways of performing that function that you're describing, sort of managing a possible scramble for lunar resources or something like that. So I think that the ideas are at the early stages of development, but there are some out there.
Thank you. That concludes all of our questions and our event for today. With that, I would like to thank everyone for participating in today's lecture. I'd also like to invite you back next month on March 5th as we host the second in our series of these bicentennial lectures titled STEM at the Elementary Level. And before we sign off, I would like to announce our winner of our drawing for today's participation, and that winner is Easton Ingram. And Easton, you are on this site here, or on our event page today. So we will get in touch with you through your email to set up arrangements for you to get that prize pack. Again, thank you everyone for joining us. We were glad you were here and hope to see you again next month.